So we're now going to look at an example of how to do regression of a model to a set of data. So let's once again imagine that we are given a set of data points that are represented here in this plot. So we have a series of x coordinates, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we, at these particular coordinates, we have individual measurements, which we're calling y equals f of x, right? So we have x that maps to y. And we're looking for a model, and which again we're going to call v of x, that somehow approximates or is similar to the given data f of x. Of course, there are many models that we can imagine come up. We're going to look at particularly polynomial models here. But for now, to begin things, let's look at a very simple model where our model will be v of x is simply some parameter which I'll call b. Right? So I'll make this model a function of this parameter b, so this is why I'm adding a subscript here. This model maps the independent variable coordinate x to coordinate y, right? So we would like to have v, which in this case is just a constant, right? It's not really a function of x. It could be, but so let's say if b is here, you can see that that particular line will not pass through the data points very well. If b is here, oops, that was incorrect. If b is here, the line will be a better fit to the given data, right? So how do we measure this fit? What we can do is we can say, for example, now let's be a little more specific. Let's call this coordinate x1, this coordinate x2. So we have the data sample at specific coordinates, and we can come up with a function that measures the alignment between a model with some particular fixed b and the data x. So let's write this model, this function that measures this alignment or this agreement. Let's call this function q, and let's make this function of parameter b. So this function can be written as, let's take the average, 1 over n. So let's say we have 10 points here. So this will be the 10th coordinate. So, and in this case, in this particular example, we have that n equals 10. And we're going to sum for, let's say, k equals 1 through n, which in this case again is 10. We're going to sum the square differences between the model, which is vb of xk, minus the data, which is given as f of xk, and we're going to square this difference, because if we didn't square, then perhaps we could have a very bad fit. For example, this is a very bad fit to the data, but potentially or here this is not as good a fit as this one, and potentially the negatives could offset the positives and still measure low error. So it's crucial that we take the square of the differences, and so this is a least squares example. And here what we'd like to do then is find the parameter b such that this sum of squared errors between the model and the data, which we abbreviate as a function of b, is as low as possible or minimized. Mathematically, we often abbreviate this statement here the following way. We say we would like to solve the following minimization problem. So we say min over the parameter b this function q of b. So let's look at what this function looks like. So we have this model, we can plug it into this function here, and this is what we're going to do next. So our function q of b will be 1 over n, sum over k equals 1 through n, this value b minus f of xk. Right? And sometimes, since we're just beginning to discuss this topic, sometimes I find it useful to expand the sums just so my brain will understand better, more intuitively what's going on. Right? This symbol sigma here, stands just for a sum, and sometimes it can look mysterious, particularly if this is your first time seeing it. So it's helpful to expand the sum in a few terms, right? So we have term number 1, b minus f of x1 squared plus b minus f of x2 squared, plus we keep doing this until the 10th term in this case, right? So because n equals 10, b minus f x10 squared, and that's, so you can see once you expand this out, right, we have just a sum of these squared terms, and each term looks pretty simple, right? And this here is the real meaning. This is just an abbreviation of what's going on. So now we have just a function which we call q of b. And you might remember from calculus, how do we find the minimum of this function? The easiest way, right, the simple way, is to find the derivative of this function, compute the derivative of this function with respect to the parameter b, and then set it to 0, and find the b that satisfies this equation. So let's do that. So again, we're going to differentiate this function q of b with respect to parameter b. And we can actually take a look at this function because it's going to be easier to do that. So let's compute this derivative of q with respect to b. So we can go term by term here. The derivative of the sum is the sum of the derivatives, right? So we can see here, let's differentiate this term here with respect to b. So first of all, we're going to keep the 1 over n outside. And this derivative here, this is a quadratic function on b, right? So if we expand this out, and the derivative is just going to be 2 times this guy, right? So what do we end up with? Here is 2 times b minus f of x1, right, times the derivative of the inside function, which, the inside term here, which is just 1, so we don't need to write that. And we can keep doing this for all the other terms, right? So let's do one more. This is going to be 2 times b minus f of x2 plus dot 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 plus 2 times b minus f of x10. Oops, we don't need the square there. So here we go. Let's write this, in the sum format once again, because it's easier. We don't have to write all the terms. We can just write the sigma for the sum. And I'm going to take this 2 out, right? And I'm going to put the 2 over n here. 2 over n. And what do we have here in the middle? So we have a sum from k equals 1 through n, 10 or n, right, of these terms here, which is b minus f x k. This is our derivative of the function with respect to b, of b with respect to b. And again, what calculus taught us is that if we would like to find the minimum of this function, one necessary condition for that minimum to occur is that this derivative has to be 0. So let's set this to 0. And we have to find the equation that solves this. So let's rearrange this a little bit just to see what this looks like. We can write the sum here as 2 over n times the sum of k equals 1 through n of b minus, because now I'm expanding the second part and that has a minus in front, so minus the sum where k equals 1 through n of f of xk, and again this has to be equal to 0. So let me write this on the following page here. We're continuing this expansion here. So now we can write this as two individual sums, right? So 2 over n sum over k equals 1 through n of b minus 2 over n sum over k equals 1 through n of f of xk. And again, both the right hand side should be 0. So now, right, so this b here, I can take this out, right? So the sum here is going to be written as 2 over n, but I'm summing n times b, right? So this is n because times b, right? This result here, summing n b times, summing b n times equals to n times b. And I'm going to go ahead and move this guy to the other side, so a minus becomes a plus, and this is going to be equal to 2 over n sum over k equals 1 through n f of xk. Again, everything relating to this is given. This is the data points that are given to you, right, for this problem. So of course we can cancel, you know, this multiplicative term that happens on both sides here. So we have that n times b equals the sum k equals 1 through n f of xk. And we would like to find the value b again, right? So we can divide both sides by n, and we have that b is going to be 1 over n sum over k equals 1 through n f of xk. Right? The thing to see here is that there are many things to observe, but one important thing I would like to call attention to is that this solution here is possible because we have a system of linear equations here. Of course, in this system, we have just one equation and one unknown, which is b. Right? But we will do this again pretty soon, and we'll generalize to more equations with more unknowns. But you can see that because we have n equations and n unknowns in this case, and well, we have, you know, one equation and one unknown, so we have a linear system here, and it's a linear system because the value that we're seeking, b here, only appears with a multiplicative term in front of it. There is no sine of b, there's no b squared, no square root of b, or any nonlinear thing happening to b. So this is a linear system of equations. Of course, we have one equation and one unknown, and this is why it was possible to apply a very simple technique to solve for b. And of course, we can graph now what the solution is. And by the way, we also observe that the solution for b is simply the average value of the data points. I'm summing these data points and dividing by n. So we can plot this average value here. Let me choose a different color. Let's choose green maybe. Right? And this is going to be the best match of this model, which is just a constant. I tried to draw here our model v of b of x equals b, with b defined as we've written down here, right, as the average of the given points. This worked really well, and we'll expand upon that a little bit later. This worked really well because if you look at this term here, we have a sum of terms, but each term really is a quadratic equation. So each term here is a quadratic equation on the unknown b, right? If you expand this thing out, it's just a regular quadratic equation. And of course, the sum of several quadratic equations is itself a quadratic equation, right? So this whole thing here is simply a quadratic equation, which is pointing up in some ways. So when we would like to find the minimum value of a quadratic equation pointing up, all we have to do is differentiate this function, right, to compute the first derivative, and find where this first derivative is 0, which will be roughly in this point being drawn here. So this is a very simple example of linear least squares regression, right? It's linear because we're seeking to match a model to some data, and the model is linear, meaning that unknowns, the things that I'm looking for to determine in the model, in this case it was just b, happen linearly in this model. There is no b squared, there is no sine of b, there is nothing more complicated going on.